You are looking at a three-dimensional model of the capsid or protein shell of poliovirus. The structure of this virus was determined in 1985 by X-ray crystallography, but these movies are showing how the molecules in the viral shell might move in short periods of time, in nanoseconds. They even show how the viral RNA might fit into the shell and how it might move about. These simulations were created by Jason Roberts, a virologist at the Victorian Infectious Diseases Reference Laboratory in Melbourne, Australia. I recently visited Jason to learn how he develops these simulations. I first visited his laboratory in the newly constructed Peter Doherty Institute, where he displays the simulations on a very fast computer.
So we can actually look at all this stuff in 3 dimensions as well, so in depth perception, so you have to wear really silly glasses, unfortunately.
So that something just happened. Is this connected to the...
It's now triggered. Yep.
How does that work?
So there's a little infrared transmitter here, so the light is green. I've got 3 simulations I'll show you, which I think you might be interested in. So the first one is just a virus. It's type 1 polio, Mahoney strain. Mm-hmm. So I based it on the crystal structures from Jim Hogel's group back in 85, and I think they refined it later on. So I rebuilt that, and I did a very simplistic RNA model in the core. So essentially it's like a snake in a basket. It's just rolled helical RNA, so it's basically just coiled with inside. So if you were to grab, say, the 3' end and pull on it, the whole thing would then just come straight out. 2-fold axis of symmetry.
So you're modeling what you think the RNA would look like inside.
I tried a whole heap of different ways of doing it,
and
none of them worked. They were really unstable, and they did all sorts of crazy things. And I've got quite a funny one where the virus just disintegrates. And it's not very happy at all. We've got another one where Mike Kuiper, who you'll meet later on, he's a colleague that's a computational biophysicist, and he's really clever. He managed to actually get the stem loop structures, all the predicted structures as well. So he spent about 6 months modelling that, and then the problem is transposing it across into a capsid, and that's where you run into trouble with, if you don't have the right level of magnesium, they'll just unfurl and do some crazy things. And so we've had a bit of trouble getting that to be stable within the virus capsid itself. But we're going to keep working on it anyway, because it'd be good to have the 2 different models to compare.
And how long does that take to calculate?
So, using around 50 trillion calculations per second, so that's on the supercomputer, that would have taken me about a month of continuous calculations.
Wow.
So that's a lot of supercomputer time, and it's very expensive. I mean, the viruses are really, really small.
Right.
But the simulations are just enormous in terms of what's been done. So this one here is derived from a 4 million atom simulation. So in this particular one, I've stripped out all the water molecules and the hydrogens, because it's for what I'm going to show you, it's not really that relevant. And that just reduces the size so the computer can handle it. Because when we first started doing the sims, the computers themselves couldn't even handle.
So what kind of machine are we...
This is one I built. So this one's... it's actually... They have fairly specific requirements. They like to be kept cool, so there's some pretty big fans in there, and there's a lot of heat. This one's running 2 CPUs in it. So
what OS is it running?
This is running Linux.
Linux, yeah.
And we've made it look like it's running Mac OS just to keep people happy. So you've got a little dock down the bottom. So it sort of looks like Mac, but it's not really. This has got 64 gig of RAM in it. So this is actually the type 1 Mahoney.
And what do the color codes mean?
Okay, so that's depth. So red is at 166 angstrom.
So those reds are the high points in the capsid, basically.
Yeah. So it'll start colouring at about 16.5 angstrom, and then the blue is at about 13.5 angstrom, just to give it a bit of depth perception. We can do all sorts of shading and things, but computationally it's a little bit expensive to do that. So that's a 0.1 microsecond simulation. So that takes about a month, as I said, to do that, and it's in a very, very short period of time. In the life of a virus, that'd be sort of watching a person for maybe an hour, I suppose, doing something and trying to work out what they're doing. We really want to watch them for a week or a month or a year to really know. So we can break it down. I'll turn these ions off on the outside so we can actually see the structure. And we can do all sorts of an angled representation, so we can change this to a sort of more traditional looking surface rendering.
Mm-hmm.
So you'd be more familiar with those sort of things from, say, cryo methodologies. And so we can also do something tricky and say, okay, I want to cut it in half, so x is less than 0. Okay, so we just cut the virus in half.
And what are the spheres inside?
So these are all the magnesium ions, and so what I'm doing here is just I've set the visualization up so it's so that it we're saying, okay, show me everything that's within 5 angstroms or half a nanometer of the RNA at the end of the simulation. So what we can do is go back to the beginning of the simulation, and those ions that were outside, you can now see they'll make their way through. So when we run the simulation, we can actually track. Okay, so that one just went down the pore. So if we go back here, so this is the RNA.
So that's just RNA.
Just RNA.
And the color
is by 5' to 3'. So you can just see how I've wrapped it up. I've essentially just coiled it down like this.
Yep.
Get up.
Do you have a computational background?
Not really. I was a musician.
So
when I left school, I had dreams of being a musician and all that sort of nonsense. But I had an accident in my senior year, and it left me with nerve damage, so I couldn't play anymore.
What was your instrument?
Guitar. So I was going to go to the Conservatorium of Music and learn classical and flamenco and all those sorts of things, and it just didn't happen. So I ended up doing robotics. So that was as an electronics engineer, which was sort of sprouted out of this sort of little side chain of the music. I was fixing guitars, working in a music shop and fixing PA equipment and all that sort of stuff. So I've always been like the hall guy that goes and does all the audio visual stuff at the school and set up for the assemblies and things. So I've always been that sort of way inclined. And so I worked out how to fix amplifiers and things. And one of the guys that was running a shop just said, "Look, come and work for me for a while." And he ended up creating an animatronics and robotics business, doing custom built singing, dancing robots and things. So I was just, we were etching our own circuit boards and designing, circuits and things. It was really, really cool fun, really, really great fun. And you'd come at the end of it, 3 months, you'd have this 8-foot tall robot that would sing and dance and do all these crazy things. So it was like being at Disneyland. But we also did custom electronics and stuff. So in that sense, I think I've always been exposed to that sort of stuff. My father was a systems analyst, so he worked with computers all the time, so they've always been around.
Yeah.
So I've always, I think I was about 10 when I wrote my first program or script, and that was really nerdy, was to map the positions of the moons around Jupiter. Yeah, super nerd.
You're doing the same thing.
Yeah, basically.
Moons around polio.
Yeah, exactly. And looking at lines, very similar sort of stuff.
So because to do this, you need to write
scripts and things.
Right?
Yeah, it's a lot of checking because you're talking 4 million atoms.
And what kind of language do you use for that?
TCL for most of the stuff. I'm trying to get into Python, which is a little bit better.
Yeah.
Ultimately, we could be doing Fortran or something, which is really efficient. But yeah, that's just too hard. Most of this stuff is all. I try to use open source or free software as much as possible because it's really expensive.
Right.
University of Illinois, so Klaus Schulten's group developed all the nanoscale molecular dynamics software. So that actually runs on the supercomputers, but we can also run it on this. And the visual molecular dynamics, that integrates with the software as well. So it's all free to download as long as it's academic. I didn't get into virology originally. You're going to love this. The thing that got me into virology was actually a movie. I bet you can't guess which one.
Was it Outbreak? That horrible virus movie, huh?
It's about the same time as Hendra and Nipah came out, and it was just all that.
With Dustin Hoffman.
Yeah. I just thought, I want to do that, because I was originally studying anatomy and physiology because I wanted to actually move from the robotics to prosthetics to start thinking, I can do robotics, so why can't I start designing some prosthetics? So I started studying that to try and get a better idea of it and anatomy. But it was quite funny to see this movie and just go, oh wow, that's awesome, and then there was Hendra and Nipah and like, oh, that's what I want to do. I want to get into that, So I just went into this whole completely different area, and got into pathology. So that's where it all started.
Okay.
Yeah,
it's good. It doesn't matter how bad the movie was; it got you interested.
Well, that's true. Yeah, that's true. So, and that's where saw your work with the cDNA constructs and
Right.
the polio stuff, so I thought that was really fascinating. So I thought, well, going from two-dimensional sequence, can you go from 2 dimensions into 3 dimensions?
Mm-hmm.
And so, well, yeah, you can. And so that was a few years ago. And then I thought, well, what about the 4th dimension, time? So can we go from 2 dimensions to 4 dimensions,
Mm-hmm.
3 dimensions to 4 dimensions? And so here we are. We've managed to do that. So it's a reasonable proxy. The RNA seems to be behaving itself. It's
Mm-hmm.
not doing anything crazy. It's sitting there. It's making the contacts that are known. So we can actually look at. So this is the VP1s. As they're arranged, it gets a bit complicated. So I can actually do that as just cut one of the planes out so we can see inside a bit better. X. Okay, so we can actually see where we've got interactions. So contact points. And you can map them out. So these are basically helices, although most of them have unfurled a bit. So that's the missing amphipathic helix that's on the N-terminus.
Mm-hmm.
We can look at the other chain, so VP2. So we'll say NX is less than 0. Cut that one away. Chain 3, and X is less than 0. Get rid of that one. And then, of course, poor little VP4. I know I shouldn't imply sentience, but you sort of get a bit attached to them, I have to say. And so VP4 is a really mobile element. It moves around a lot, and I can understand why a lot of the crystal structures don't have VP4 in them, because it's crazy. And same with VP1. VP1 tends to have this movement across 90 degrees across the surface of the RNA. So I can probably make that RNA look a little bit better by change that from a trace to a ribbon or something, so it looks a bit more. Okay, that's a bit disordered. So you can see you've got all these different ways of representing the molecules. That's quite useful. And then we can bring it to life and make it actually do stuff.
And so you said this is a package that's available
Through the University of Illinois.
University of Illinois?
Yeah, so I went over there and spent a bit of time when I went to the CDSC in 2012. I stopped by the University of Illinois for a week. And just given that these are really big simulations, there's a lot of problems with running them that you run into. Just fundamental things like I tried running them on a 32-bit Windows system and it just couldn't handle it because the file sizes were too big. So in the end, what I actually did was run one of the simulations on a micro SD card.
Mm-hmm.
So it was one of those things in your phone, memory card.
Right.
So I loaded an operating system on there, a Linux operating system, put all the simulation software on it, and then booted the computer off this little card. And that got around the limitation of running Windows, so I actually ran a Linux operating system. And I can actually run it on my workstation, the computer here. It's about 10 days per nanosecond of simulation time, as opposed to 3 nanoseconds a day up to 15 nanoseconds a day on a supercomputer.
So when the movements we're looking at now, what's the time period?
So the time period on this one is, these will be 1 nanosecond time points.
Okay.
So the actual one is 0.1 nanosecond that I've got, but the file sizes are so enormous that it would be really quite kludgy, and the computer would be struggling. You can already see that this is a $15,000 computer, and it's made out of bits and pieces over time, the parts that we need. You can already see that it's struggling to keep up with the amount of data that's being streamed through it. So the interesting thing with this simulation, though, is this has actually got a drug in it. So we've got our palmitic acid, which is sitting in the hydrophobic pocket there. And then in the centre we've got a little nest of myristates, which are covalently bound to the N-terminus of VP4.
Right.
And so they are quite happy to sit there in that state, but if you take the RNA out, they're not so happy. They'll start to just basically eviscerate themselves.
And the other molecule is the drug, right?
So that's the one in here. So what we'll do is go back to the time point 1, and we can actually just play that through, and you'll see the drug molecules skating around and making contact. And some of them will, in fact, so you can see this guy here is basically burying itself in where the hydrophobic pocket is, and it's being joined by another partner. So we can actually spin this around and have a bit of a look. I might just reduce that size of those atoms there because they're a bit big. So now you can actually see the lipids inside their pockets. So we've got a nice little canyon, so a 5-fold, a nice mesa. There's our propeller here. So the usual structures. And so one of the things I can do is look at what's the electrostatics distribution like. So this is in a saline solution at 37 degrees. So we can actually do some calculations. So I'll switch that off and switch this one on. And you can see how I've coloured it. It's a bit hard to sort of work out. I'll just turn this just for place marking. Turn our licorice off and I'll put our quick surface. So you can see I've skinned the outline of the virus. Yep. And then we've got these areas. So there's the 5-fold, the mesa. And that's a little bit more electropositive than the surrounding canyon, which is a little bit more electronegative. And it's a fairly consistent thing that we see across all of them. So same here, more electropositive with electronegative around here. And so I tend to think that with the drug molecules and the distribution of charge combined with the hydrophobicity, it's like they're being channeled away from this area and then bouncing back this way and finding sort of that central point. It's
so
gone
this
in.
is polio receptor, and you stuck it in a membrane.
I have. So now I've just cut the membrane out here
so you can see
that. So we can actually colour this by hydrophobicity and charge. So I'll just do that now so you can see the hydrophobic components. So in white is the hydrophobic components, and then you've got polar uncharged, and then you've got your acidic and basic residues in the blue and the red. But so you can see that the hydrophobic component actually traverses the membrane.
Right.
So this has been going on my other computer. I've got a little server, like a little 2-unit rack, which we can go and have a look at later on. And that's got 4 of those Tesla cards in it. So at the moment that's running at 2.4 teraflops. And we're hoping to be able to get that closer to 10 teraflops. So when we run this sim, so we can see that it holds its structure pretty well. Now this little tag here,
that thing at the end is the very end terminus.
right? And I haven't seen that in any of the crystal structures, and I don't know if it exists in vitro or not, or in vivo. But what I did, I just thought, look, I'm not going to exclude it, because this is how we've done the virus models before, is you can actually tag it on the end, run it for a period of time and allow it to adopt whatever conformation it wants to do. So, well, I'm trying not to give it sentience, but it will follow a path. And you can do multiple replicates of this until, and it will just continue to either go that way or other ways. So in this particular instance, you can see I've just basically, initially that was the helix just running in a straight line, but it basically unfurls itself, folds itself up into a little hairpin, and then tucks itself up underneath.
So that is in the sequence of the receptor, but it's not in any of the structures.
None of the structures actually have it. So it could be a fairly mobile element that's just not been able to be resolved, or I don't know, given that it's hydrophobic. Is this part of when it makes contact with a cell, does this actually then, is that a transmembrane component? Is this receptor lying down with a transmembrane component? You know, there's so many things that I don't know about this particular receptor. I don't think anyone really does. I don't know. I haven't spent much time looking through the literature, but I think you would probably know more about this than I would.
No one knows anything about that for sure. I know that the virus binding part is on the other side. That little beta strand right there.
Yep.
Yeah, that's the virus binding part.
Well, that's really interesting, because I do wonder what role, if it's there at all, if it really does exist.
So the
or is it cleaved?
The movement that you see is, and the way it's arranged in an alpha helix, that's based on the properties of the amino acids. It's a prediction, right? Right.
And so now it's just undergoing the physics and just. So it was originally I created an alpha helix similar to this into space, but it's now unfurled itself and basically said, no, that's not the conformation that's appropriate. And it's now adopting another conformation. So you need about 10 to 100 nanoseconds for secondary structural elements to form and to correct themselves. So we've got another 50 or 60 nano. I'm running that at the moment on the machine downstairs. And so we'll see how that goes. I'm just going to continue to run it just for the next month or two and try and get as much time out of it as I possibly can, just to see what that does.
insert into the particle, right?
That's
Once the
what I'm
particle
thinking.
binds, that could stick in and do something.
Being hydrophobic and given the hydrophobic nature
So
of
an
drugs.
interesting experiment. So as you know, if you just combine the receptor with the virus, it encodes. So it would
Yep.
be interesting to remove that sequence and do the same experiment and see if it doesn't uncoat.
Mm.
That would be,
Actually, that's, yeah, no, you're right.
it's doable. Yeah.
That would be very interesting.
Because the binding site is on the other side, so that should not, removing that should not interfere with binding. So
that
it
would
could
be over
block
there.
encoding. Right?
So, yeah, what would it actually be doing? What would this hydrophobic segment be doing on
So
this
that
other side?
that is hydrophobic. It's white on your
Yes.
scheme there. Yeah, that's interesting.
That was Prof. Lawley bought that for me.
Next, we walk to the supercomputer that Jason uses to create the simulations. Its formal name is the Peak Computing Facility, and it's part of the Victorian Life Sciences Computation Initiative. Senior Systems Administrator Chris Samuel gave me a terrific tour of the hardware. A word of warning, though, it's very noisy in the facility.
So there's actually 3 machines in here that we run. The biggest, of course, is the Blue Gene, which are these 4 racks here.
So this is the processor here, or just drive?
No, this is just CPUs, CPU memory, and interconnect. And it's the interconnect is a 5-dimensional torus. I have no problem thinking in 3 dimensions, but this is all the fibre you can see. And what you have here are cards that go in. If we could pull one of these out, you would see 32 compute cards on each one. Each compute card's got 16 cores and 16 gigabytes of memory. And each of these plugs into a mid-plane, and then you've got a symmetrical setup on the other side. So you end up with 1,000 nodes in one rack, 16,000 cores, 4 racks, 65,000 nodes, and about 64 terabytes of memory. The main thing is also they're aiming for energy efficiency. So you've got a lot of relatively low powered cores, so 1.6 gigahertz. But the idea is that you are using them in parallel with MPI programs, or you're running lots of single node jobs. It's all water cooled as well. So we've got a water cooling, so there's a cold and a hot. So cold inlet comes in, it's circulated around the board, and there's a clamp that connects the card to the water. So heat transfer, and then hot comes back out and then returns to the CDUs. So they're closed loops. When this came in 2012, we rolled 2 racks in on one weekend, 2 on the other. They were part assembled, which meant there were only 1.8 tons on the rack. When they were fully assembled, they're 2.2 tons with the water. So it's a reinforced floor under this section. Mid-2012, we rolled in the first 2 racks. I worked out on the back of the envelope, that was about the same as the 5 machines in Australia on the top 500 put together in theoretical performance. Probably not a great one to lift, but you can see you've got the inlets to racks over here and outlets, so it's never obvious from looking at them which is the hot and which is the cold. This is cold. Even though it's insulated, it's still a degree or 2 cold from that in there. And then you can see more of these cables here.
What's the orange
Power. This is power coming into the room. 50 mil or 500 mil cable, and switchboard rated at 1600 amps. the really scary number is the short circuit, which is 40 kiloamps for 1 second. I would not like to be here if that ever happened. We've got two Intel based clusters as well. So this is our oldest. This is called Mary. It's a 2010 era Halo based machine. It had a memory upgrade middle or early 2012. So most of the nodes have 48 gig of memory and about a third have 96 gig of memory. Middle of last year we had this Intel machine arrive. So this is a Sandy Bridge based cluster. For comparison, each of those nodes, and there's 80 nodes in that rack, have 8 cores. These nodes have 16 cores, but the memory is 256 gig per node, with 3 nodes with 512 gig. And that reflects a lot on the bioinformatics use.
What are the orange cables?
So most of the orange you see is InfiniBand. These two here are 10 gigabit Ethernet for the login node. So this is a login node, and this is also a login node. So they got dual active 10 gig, and InfiniBand is on these is QDR, so 56 gigabits. But the important thing with InfiniBand is the latency. So when you're running parallel jobs with MPI, the higher your latency, you spend more time waiting for messages, and your code is less efficient. So we can get really good latency on here with the InfiniBand, and so your code is more efficient than you would be using gigabit or 10 gig Ethernet.
So these are in use at the moment?
Yes.
It's doing something?
Yes, yes. In fact, I will demonstrate that. Come around the back. So virtually everything in here is water cooled, other than the tape library behind you and the UPS. But that's, that feels a little warm at the moment. However, if we open the back door and you put your hand in there,
Hot. Quite hot. Because it's working, right?
yeah, exactly.
So if they weren't processing, they wouldn't be hot?
Yeah, yeah. So the rear doors do really well at taking that heat out, getting it to the CDUs, and then out.
There's water flowing through?
Yes, yeah.
It's water cooled, right?
Yes, yes.
Yeah.
So these are the water pipes.
Yeah.
So the blue jeans is water cooled by actually direct connect to the nodes.
Yeah.
Everything else is water cooled with these doors where the hot air is forced out through this radiator grill, and then you get a heat transfer to the water going through it. And then that comes back to these what are called coolant distribution units here, CDUs.
So these are just for cooling?
Yes. So they connect the closed loops in the room to there's a large buffer tank behind that wall, and then up to the top for the chillers. We have about a petabyte of spinning disk, which I'll show you in a minute. And then we've got the tape library, because a lot of the projects, we have about 4 petabytes worth of tape capacity here, and it's not fully loaded. This is LTO5 library, so not the very latest generation of tape, but we can get about, I think it's about 800 gig or 1 terabyte onto each tape uncompressed. We run with compression. This is the disk storage side, and what you've got here is a pair of controllers which are working together. These are connected by InfiniBand to the storage nodes, and they connect by SAS cables to each of these enclosures. So there's 6 here, another 4 here, which are connected to these pair of controllers. So 10 enclosures. Each enclosure has a lot of drives. I can never lift this part up.
Each one is a drive, right?
Yep, each one's a drive. There we go.
And the 900 gig attach.
So these are 900 gig attached drives, yes. So these are high-speed drives, and low latency as well. So they're 10,000 RPM drives. So the seek time is pretty low.
How many total drives are here?
Well, you've got 60 drives in an enclosure, 10 enclosures on the controllers. So that's 600 drives on this pair of controllers. On the other side, I'll open this one. This bottom four, and then the 6 here are connected to a pair of controllers there. Those have 600 1 terabyte SATA drives in them. So 600 terabytes plus another 500 odd here raw means we have about 700 terabytes usable, not all of which has been commissioned. There's a small section we keep aside for testing.
Why do you need so much storage?
We have a lot of users, basically. Finally, these are the storage nodes that connect to that disk and then present it to the clusters. And we use a file system called GPFS. And with that newest Intel cluster, when we were doing the bring-up tests, we were able to drive this at about 12 gigabytes a second, which was faster than DDN, the people that make the storage, claimed you could do. So we were quite happy to beat them benchmark. What we do have are the old-fashioned KVM switches. So if we need to do anything here, we can do that on these systems. And you can swap between various things. When you're working on the Blue Gene and you need to pull out one of those node boards, they are very heavy and they're also full of water. And so this tool here is a powered lift. They take this over, they'll lift it up to the right height and they drag it out and put it on that tray. This is the UPS. So the UPS isn't for the compute. This is only to support things like the management nodes, the storage, the tape library, all the infrastructure and the network stuff.
So what's the backup for the CPU?
They're on filtered power. The power out here is actually really good, mainly because we're actually pretty close to a number of hospitals. So we generally don't have problems with power. So these are all converters, there's switches, and then these are the batteries.
What do we got here?
These are the water control, the water distribution units, yeah.
Got it. Computer tool.
They're the company who do this.